So section 2.8. There's only four questions I have planned for. Now these are a little bit longer because they're word problems. So this is where we can take a lot of the ideas of the derivatives, everything we've talked about, and actually apply them to different scenarios. So in these kind of problems, you'll want to visualize them in some way. So you want to have some form of or you want to make sure you understand what it's asking first, as best as you can. What are we trying to calculate? What are we trying to find? Then we can draw a picture, and we'll do that in a lot of these. When we start dealing with quantities and rates of change, we need some sort of letters to stand for these things. So we're going to introduce some notation in there to try to get all the quantities. So our questions in this section are going to be all dealing with quantities that are changing with time. So rates of change and so forth. So we want to have symbols for all these quantities that we're working with. All of these questions, so the name of this section is related rates. So one of the very first examples we deal with is the idea of a balloon. If you're putting air into the balloon is expanding with at a certain rate. So what kind of things could be expanding on a balloon? Well, of course, air is going in, and we can measure the rate at which the air enters the balloon. But then the balloon has lots of other dimensions to it, right? So feeding air into it changes its dimensions, in other words. So its surface area is one, volume would be another one. So there's lots of different quantities that are changing in the dimensions of that balloon as we feed air into it. So we have rates which are related to one another. Rates of air flow relating to the rate of change of the dimensions in the balloon. So that's why we call this related rates. So once we get the information we need from the question, we have all the symbols we need for what we're trying to solve for. We want to have all the given information that we know as rates. So, and the required rate. So if we're feeding air into a balloon, we'll go ahead and express the rate at which the airflow in terms of a rate of change. And then the dimension we're trying to know the change of, we'll give it also some symbols too. And if we know any numerical information about the rates of change, we'll usually wait till near the very end of all our work to actually use that information, all the numbers that we have, rates of change and so forth. So the very first one here, it says air is being pumped into a spherical balloon so that the volume is increasing at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Okay, so obviously if a volume of a sphere is growing, radius has to be growing too, right? So these two rates are connected to one another. So we have to figure out how are they connected to each other. The connection is going to generally be found by some formula which connects the two together. So if we're dealing with this situation, I don't think I can draw a sphere. Does anybody here know how to draw a sphere? I'm totally not good at doing that. So can we just sort of imagine it as looking from above, I guess? I'm kind of tempted to try. Kinda? Can you see it good enough? So we know the radius, call it R. The volume. Okay, these are the two things we're dealing with here. Volume, we'll call it V. Radius, we call it R. We're given the rate of change of volume as 100 cubic centimeters per second, and the wanted So wanted quantity is the rate of change of the radius when the diameter equals 50 centimeters. Okay, so that's kind of the summarizing everything. So let's think about, now that we've got these letters standing for the volume and radius, let's talk about their rates of change and the notation we want to use for rates of change. As a derivative, I've talked sometimes about this dy dx, right? And I may have mentioned the other day delta x and delta y, kind of as a connection between those. So when we say dy dx, the quantity that is changing, or that we're measuring the change of, is this variable y. And we're measuring it in relation to how x changes. So if we look at these variables here, okay, if I write dv over dr, okay, what do y'all think I'm saying by that? Exactly, yeah. So this is basically saying the change in volume. Okay, that's on top, right? So the change in volume as the radius changes, or the derivative of v with respect to r. That could be the rate of change of v with respect to r. Okay, I'm not dealing with time, but it's obvious that the volume is changing if r changes, right? If r increases or if r decreases the radius, the volume has to subsequently also change at the same time. So what about, now we have the derivative of r with respect to t. Okay, what is this measuring for us? It's going to be the change in, right, rate of change of r with respect to time. Okay, so it's going to be kind of how we measure these kind of things here with respect to time. All right, so for volume, dV dr is that 100 cubic centimeters per second. And this is what we're actually going to be trying to get to here. Okay, dr dt is what we actually would like to find in the long run, the actual rate at which the radius is changing when the diameter is 50 centimeters. Okay, so what now the next part we need is we need a formula which connects V or R with V. Okay. Yeah. Oh, yeah. Is there a formula that has R and V both in it at the same time? Probably not a formula we have on the top of our head, right? All the volume formulas and all that stuff. But the volume formula for the sphere will uses radius within the calculation of volume. So volume V is 4/3 pi r cubed. Okay, so this is the formula we need to have. So in order to go from this step, we're going to take d over dr of both sides. Okay? So a while back we did something called implicit differentiation, right? Implicit differentiation, we could take the derivative of both sides of the equation, and then we had to do some work with that. So if I take the derivative with respect to r of v and the derivative with respect to r, 4/3 pi r cubed. How do we take the derivative of v? Yeah, you only take the derivative of like x, it's just 1, right? So this is actually just going to be 1. But since we're taking the derivative of with respect to r, I'm going to also have dv dr. This is like what we did with dy dx. So the r and the v don't match each other, so we can't just go straight to the regular derivative. We have to include that extra term. This would be dv dr. Okay, and then what's the derivative of 4/3 pi r to the third? We have the 4/3 pi here, right? What's the derivative of r cubed? 3r squared, yep. So if you do the multiplication here, these 3's are going to cancel each other. And you'll get dv dr equal to pi r, or sorry, 4 pi r squared. Okay. Oh wait, I made a mistake here. What did I do? Okay. There needs to be, and this is going to be kind of going against what I told y'all the other day. Let me see if I can explain what that means. Let's make it this way here. No? I have to put a dr dt on the end. Let me see if I remember why that's the case. Yeah, sorry. Okay, let me scroll back for just a second. So let me correct myself on one thing, okay? When we have this up here, I think I needed to say this is dv dt. Okay, instead of r. Okay, sorry about that. So if we're measuring things with respect to time, then down here I need, instead of taking d dr, I need to take d over dt instead. Okay, this will make more sense then. So let's do d over dt instead. Not a big change. So that's going to be dv dt instead. Okay, and now it makes more sense why we need to put the dr dt here, right? Yes. Because I'm taking the derivative with respect to t, but of v and of r. So we have to include that extra term to include the dr dt and the dv dt. Okay, does that make okay sense so far? Okay, so that's looking better. Now, when we have a situation like this, where we started up above, we have measurement for dv dt. We also have something for diameter 50. So we can actually substitute in for 2 of the 3 unknown quantities here. So if diameter equals 50 centimeters, what does r equal to? 25 centimeters, yep. So we basically have here r equals 25 and dv dt is the 100 cubic centimeters per second. Okay, so we can substitute these two values into our equation, and then we can figure out what the dr dt is at that point. So we're going to get 100 equals 4 pi 25 squared dr dt. So that's going to turn into, what I'm going to do is I'm just going to go ahead and divide both sides by 4 pi 25 squared. Okay, and what you're going to get is dr dt is 100 over 4 pi 25 squared. So rather than doing the calculations, I've just got to put it all together, if that's okay with y'all. And I'll just divide both sides to move that over, leave it like that. That's something that we can then approximate. I'll scroll down just a little bit. Dr dt is approximately 0.0127, okay, in this case centimeters per second. So let's kind of think about how we did this here. So we started out with those initial quantities, one of them measuring the diameter, a certain moment of time. We also had the rate of change of volume. So we had to take the derivative of both sides of the volume formula so that we could get dr dt here. And with dr dt, we can substitute in those numbers. So now we know what the actual rate of change of radius is with respect to time. Does anybody have any questions on that one? Okay, so let's take a look at the next one. Okay, this one goes with a ladder, 10-foot ladder, rests against a vertical wall. The bottom of the ladder is sliding away at the wall at a rate of 1 foot per second. So how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Okay, so the situation here, we got vertical wall, got the ladder resting up against it, and it's sliding down at a rate that we don't know, so many feet per second, and the base of the ladder is moving away at 1 foot per second. And it's a 10-foot long ladder. Okay, so let's label we basically got our right triangle here, right? So first thing to do is go ahead and give some letters to the sides here. So we've done two unknown sides of the right triangle. We'll call those X and Y. So this is moving at exactly 1 feet per second when 6 feet from the wall. Okay, so we have to have all that information to make this work. So we want to know basically how quickly is this distance changing. It's shrinking obviously as the ladder slides down the wall. This one, we know the rate at which that side or that distance is increasing at exactly this moment, 6 feet from the wall. So let's talk about our notation. Okay, so since this is a rate of change, what variable are we measuring the rate of change of here? if I call that side x? This side x is changing, right? At 1 foot per second. So how could I say the rate of change is a derivative for this side? Yeah, dx. And what is it changing with respect to? dy, okay. So let's think about it for a second. So it's changing with 1 foot, right? Per.
Oh, so
It's dt. So t doesn't show up anywhere here, does it? And on our variables. We have to kind of think about, okay, what is it changing with respect to? It's changing with respect to time, right? So that's sort of the seconds. The seconds are the units, in other words, of time that's being worked with. But we never give it assign a variable to t. It's just sort of a concept that we're using as part of this. So what would our dx dt, the rate of change of x with respect to time, be equal to? 1, yeah, 1 foot per second. You got it. Okay, so what are we trying to find? Now we know this is 1 foot per second when that side of the triangle x is equal to 6 feet. Okay, now what derivative are we needing to find here? We know dx dt. We want to know you got it, yeah, dy dt. Because y is the side of that we're concerned with here, the one that's telling us how far away the top of the ladder is from the ground. So this is the one that's sort of our goal at this point. Okay, now we need a formula to put these variables together. What formula can y'all think of that takes x and takes y in a right triangle and puts them together? Pythagorean theorem. So you're going to have x squared plus y squared equal to hypotenuse. Hypotenuse we know to be the length of the ladder, so that would be 10. Okay, so that's our formula. Now we need to move from the formula into our rates of change, our derivatives, right? So once you have your formula, take the derivative of both sides. Okay, we're going to take the derivative with respect to time, since we're dealing with rates of change in time. So we're going to go d over dt, x squared plus y squared equals d over dt 10. And this looks very much like the implicit differentiation we did with x and with y. Okay, so starting off, what is the derivative of the right side? Derivative of 10 is 0. Yeah, so that's just 0. What's the derivative with respect to t of x squared? 2x. And since we're taking the derivative of t, we have to put an extra term there. Yeah, it's going to be d, and d of, what did we just take the derivative of variable-wise? X. Yeah, so on top is the one that we just worked with over dt plus 2y dy dt. Okay? Again, I'm only including that term because t is not the same variable as x or y. It's a totally different variable. Okay, now do we have numbers to plug into this formula now that we got to this point?
We have 1.
Do we have a variable for x? X is 6, right? We don't know. We know dx dt, right? That would be 1. Do we necessarily know y? We haven't said it just yet, or nor dy dt. But if we know x at this moment, can we figure out what y is?
Yes.
We can. So let's find y. Okay, so we're going to have x squared plus y squared equals 10. So that would be 6 squared plus y squared equals 10. So So let's see, 10 squared. Oh, I did make a mistake there, didn't I? Should be 10 squared. Yeah. Sorry about that. It comes out the same derivative-wise, but it makes a difference here. Okay, so y squared, I'm going to get 36 subtracted from 100. See, 64, yep. We're dealing with distance here, so we don't necessarily have to worry about plus minus, right? So while I'm taking the square root of both sides, technically I'd have to do plus or minus in general, but here it doesn't matter too much. So y equals 8. Now we can substitute that in. So we're going to get 2 times 6 times 1 plus 2 times 8 dy dt equal to 0. Okay, and so that's going to turn out to be 12 plus 16 dy dt equal to 0. If we do the solving for dy dt, subtract the 12, divide by 16, be negative 12 over 16. That would be negative 3 over 4, or negative 0.75. And in this case, since we're measuring it in feet per second, that would be negative 0.75 feet per second. So this situation is going to boil down to, we know that one side changes at 1 foot per second, and the other side is changing at 3/4 of a second, negative, because it's shrinking, of course. Okay. Does anybody have any questions on that one? So these are kind of your related rate problems. Okay, it's going to be kind of working this way with a lot of them that we do. We can get it. We can get some pretty complicated ones, but y'all have this one down okay? Okay, I'm going to go scroll up all the way and take a look at number 3. Do you think y'all would ever be interested in going to a calculus bowl? They had one at Commerce in April. The mathematical conference came to Commerce, and they had what they call a calculus bowl. And they had different universities sent their teams, and they all competed to do the calculus problems as quick as they could. It was kind of fun. They had questions like this on there. It's kind of neat. Okay, let me show. I'm sorry for the detour on that. I tried my hand at it once when I was an undergrad. I wasn't terribly good, but it was fun nonetheless. Okay, this is a circular, it's a cone basically, right? So I guess this could be like one of those paper cups, something like that. I don't know. It's pouring water into it. It says it's a water tank. I don't know how many water tanks are shaped this way, but anyway, so the base of the cone is 2 meters. The height is 4 meters. So water is being pumped or poured into it, however it's being fed into it doesn't really matter too much. The rate at which it's coming in, though, is 2 cubic meters per minute. So we want to know how fast is the rate of the water level rising when the water is 3 meters deep. Okay, so we have to specify at specific points. We have to take, okay, when it's 3 meters deep, what is the rate at which it's actually filling up? So let's go about doing this. Okay, so let's use some notation here. Let V be volume of the water. Okay. Let R be the radius. And let H be the height of the water. Okay. As y'all can see, this is kind of setting up with the picture that you have here on your packet. So we know the overall dimensions of the cone. We're talking about the dimensions of the water here. So if the water is kind of sitting here in the middle, it's going to kind of make its own radius inside the cone, and then it has its own height, like so. Okay, and so that's the measurements we're going to use for those. What kind of measurements do we know? Well, it tells us the radius of the cone. Okay. Also tells us the rate at which water is being pumped into it. So if we're talking about the rate at which the water is flowing in, right? So that's actually going to be dealing with volume. How much volume of water is filling the tank, in other words. So since that's volume, what I'm going to say is we know dV, change of volume, with respect to time. Okay? So dV dt, that's our 3 cubic meters per minute. Okay? Since we know that, we want to know rate at which it is rising. Okay, so the rate at which it is rising is not the volume, but which variable falls to the rising part.
Is it 2?
I'm sorry, did I put down a different 2?
Yeah,
I did. Thank you. Yeah, that was just my mistake. Sorry about that. Thanks for noticing. So the water level rising, so what part of this are we measuring its change of? The height, right. So what we want to know is we want the derivative of h with respect to time. So we can kind of draw ourselves a triangle diagram to kind of visualize the situation. This is like a cross section of the water tank as it's increasing. Okay. So this is the water level here, and this is the overall dimensions of the of that. So the formula that we want to use here is the formula for the volume of a cone such as this, which is 1/3 pi r squared h. Okay? Here, yeah, I'll give you all the formulas for these. So here's a problem that we're going to run into here. Or is it a problem? Let me see. It didn't have to be a problem. So if I tried to, all the examples I've done so far, when I get the formula, I take the derivative, right? Here's the problem with taking the derivative here. I've got 2 variables to worry about. I've got r and h. That's kind of a little more than we need to deal with. So we need to somehow figure out what one of these variables is, if we can, with what we know. So what I'm going to do is, by similar triangles, what do I mean by similar triangles? Similar triangles are in proportion with each other, right? That's what they call similar. So these two, you can actually visualize 2 triangles here which are similar. They're in proportion, the inside triangle and the bigger triangle on the outside. So what that means is the radius is in proportion with the height, h, as the proportions of the outer triangle, 2/4. Okay. This is the relation we need to break it down from one variable to the other. Because what I'm going to do here is I'm going to solve for r. Okay? You can do the cross multiply here, and you'll get 4r equals 2h. So r equals 2h/4, or that's another way of just saying 1/2 h. Okay. Or h/2, however you'd like to say that. So substituting that in, you'll get volume equals 1/3 pi, then 1/2 h all squared h. Okay. So what did I do here? I took this thing for R, okay, I put it in the formula for volume in the place of h. Okay. So if you do simplify that thing down, 2 squared is 4. 4 times 3 is 12. So it's actually going to be 1/12 pi h to the 3rd power. Okay, again, I just did some of the math here, right? This step. So got a 4th, got a 3rd, multiplied to be a 12. Okay, and now we can do the derivative. So derivative of v with respect to time, or I should say d over dt of v equals d over dt of 1/12 pi h cubed. Okay. What's the derivative of v with respect to time? Derivative of v by itself would just be 1, right? 1 dv dt. Okay, and then if we take the derivative of this, 3 has to come out to the front, right? So it's going to be 3 halves. Oh, I'm sorry. Yeah, I messed up there. Yeah. I'm making silly mistakes lately. I'm so sorry. I did this in college algebra too. Just silly little mistakes. So 3/12 pi h squared dh dt. Oops, sorry about that. 3 over 12 is just a 4th, right? So you're going to get dv dt equals 1/4 pi h squared dh dt. All right, now this is the step where we can make our substitutions. From the very beginning, we can tell what h is, and we can know what the rate at which the volume is changing, right? Okay, it says specifically that when the water is 3 meters deep, and so this is the depth of the water here for h. Okay, h is depth of the water, so when it is 3, we're pumping in 2 cubic meters per minute for dv dt. So we're going to get 2 equals 1/4 pi 3 squared dh dt. Okay, and that's going to be 2. If we square the 3, we're going to get 9. So that's going to be 9/4 pi dh dt. Be okay with y'all if I write that as 9 pi over 4 instead. Okay. Then to wrap this thing up, you want to multiply both sides. Do it this way. Multiply both sides by 4 over 9 pi. Okay, just so we can cross this stuff out here. Get the dh dt, which would equal 8 over 9 pi. That would be approximately 0.28 meters per minute. Okay, so that's the rate of of the water rising is that much, 0.28 meters per minute, when we have the volume increasing so much. Okay. Do y'all have any questions on that one? I've only got through 3 questions today. Is that a bad thing? They're long questions, right? Have I been going too slow, too quick? Has it been okay? Let me show you guys this next example. We won't finish it, I don't think, but it's kind of a little bit long. This one is kind of the extreme example. More extreme. That's what I'm saying here. So this one is a man walks along a straight path at a speed of 4 feet per second. So we know the rate at which he's traveling. A searchlight is located on the ground 20 feet from the path and is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? So the picture's been set up for us really well here, okay? So here's your 20. 20 feet, so that's the distance from the searchlight to the path he's walking along. Okay. We know the rate at which he's traveling, right? So that rate is probably going to relate to this variable x, because x is this length that he's going along. Okay. So as he's walking, x is getting bigger, right? He's traveling further away. So the rate at which x is changing is his speed, in other words. What are we trying to find the rate of change of? The rate of change is how fast is the spotlight rotating. So what variable would y'all think that's related to? Yeah, this particular situation, theta is the angle, right? So the angle that it's moving is the rate at which the spotlight is rotating. So we actually want to figure out how fast is the angle changing to tell us how fast the spotlight moves.